Keep the back down if you want to sit still. Yeah.
It's working. Oh, it's still doing.
It's like still 2 minutes. You can go and meet the professor till that time. It will just start.
Identifies me. I'll just zoom in on the. Okay. Do you think this is clear, or should I zoom in on the?
Maybe you should just zoom in on where he's teaching.
But I can't.
Yeah, you can just take this sheet.
Okay.
So I have this thing here. Start recording when the class starts, so that you'll have a copy in the back end.
Okay. How do I just press record? Now it's streaming.
Yeah, now it's streaming.
Okay.
Cool, right?
Yeah. Awesome. Thanks a lot.
That's fine. Take this chair and sit on
I'll sit here. Yeah.
I'm giving you a bag.
How?
Was it recorded?
I don't think so.
Okay. Good afternoon. So let's start. So today we're going to talk about the setup and general strategies or questions we need to solve for probably the most popular protocols used in our machine learning. It is called supervised learning. So we'll introduce what is supervised learning. To deploy or to carry out the supervised learning task, what kind of question we should consider, and we should be careful. So before we start the class, I will tell you the first homework, the homework 0, will be released today after the class through Canvas. And this homework is mainly designed for helping you to review the basic knowledge which you have learned in the first year or second years of undergrad study. So the due date is next Friday, May 9th, so because I don't want to occupy too much time in your weekends. And I highly suggest you to open your textbooks and review what is random variables, what are the independence, the definition for independence, what is condition independence, and etc. Because those knowledge are important for us to understand the content we will introduce later in this semester. So, any questions?
So the class doesn't even show up in the Canvas.
What?
The class does not show up in the Canvas.
I think I should activate the class in that class, but I didn't add any module on that. Maybe so you.
So the Canvas page is unpublished, so you have to click publish on the course, which.
Oh, okay.
Yeah. So
Okay. Thank you. Yeah, I'll publish it. And today our TA will release the first homework through Canvas, and everybody should be able to access the homework. Okay. So now let us start the class. So first, let us review what we have learned through our first lecture. So I think the most important thing is that we know what is the essence of learning, what is the kind of formal definition of learning. So learning is essentially a process to gain some generalization capability on a specific type of task. For example, as I mentioned in last lecture, if you want to obtain the capability to recognize dogs from pictures, we collect a set of training pictures which contain all kinds of dogs. And through learning from these training pictures, we expect ourselves to capture the concept of dogs, so that when we face a new picture which contains a dog which is very different from all the dogs we have seen, we should still be able to recognize this dog, not a cat, not an animal, or other things, or other animals. So learning is essentially the process to gain the generalization capability. And to have a concrete feeling about how a learning process will proceed, I introduced a simple badge scheme, right? In the conference, computational learning conference, maybe happened 20 years ago. Every attendees are required to play this game, and every attendees received a badge with name being labeled as positive sign, negative sign, and no one knows what is the underlying function is. But we ask you to collect as many badges with labels as possible, then try to work out a function which produces these labels. And if we successfully find out it, and we want to evaluate whether our function can correctly generate labels for some new names which is not in our training collections. So a typical learning procedure, which is reflected through this simple badge scheme, consists of 3 steps. The first step is training data collection. That corresponds to the collection of badges names with their labels, right? And second phase is learning. And we try to learn what kind of function which can produce the labels in our training collections. And third step is evaluation, right? And evaluate whether our function, our learned function, can have a good generalization performance. By saying generalization performance in a badge scheme, I mean whether when we're given a new set of names, a set of badges, and how can we, whether our predictions with our new functions are correct by comparing with the ground truth function, right? So this is what we have learned from the last lecture. And in this lecture, we'll still based on this simple badge scheme. And we'll use this, we'll based on this simple badge scheme to formalize our supervised learning setting. And we'll get to know what kind of factors or ingredients for us to carry out a supervised learning. For example, we'll know what is our instance space, or in other way, what kind of right features we need to extract to effectively represent our instances and to be better processed by our machine learning algorithm. This is a very important step. What is the label space in the supervised learning? That consists of, that actually determines what exactly the prediction task is, and also determines what is specific type of our supervised learning task. And each type of supervised learning task will correspond to a set of different specialized learning algorithms. And also an important concept we should learn about supervised learning is the hypothesis space. And we'll know that the choice of hypothesis space before we run the learning algorithm is very, very important. And there is some pessimistic side for choice of hypothesis space. That is, we cannot 100% sure the correctness we choose for the hypothesis space, except a few ideal or toy problems. And what kind of general strategies we should use to choose a appropriate and practical hypothesis space. So that's pretty much what we're going to talk about in this lecture. So let us review the simple badge scheme again. And suppose now I have collected a set of training badges with the labels. So our task is to learn a function which can produce the consistent labels with our with our training labels, right? And then if we are confident about our learn function, we can apply our learn function to label some new names like Peyton Manning or Eddie Manning. So I'm going to ask you again to work out a function, or in other words, to learn from this set of training examples. So can anyone share their thoughts or any ideas? This set of training collections are different from
When the number of letters greater than 1 is negative.
how do you work on it?
Just count the number of first name letter.
Okay. Any other ideas? Yeah, I think you are smart because this is also what I work out from this sample for this collection of training badges. So let us look at this function. Very simple function. It says if the length of the first name is less than or equal to 5, then we'll produce positive label. Otherwise, we produce negative label. We first need to examine whether our functions are consistent with our training labels, right? So let us take a look. So in our first instance, which is Claire Cardio, and the first name is Claire, right? And what's the length of the first name? 6, right? So it is bigger than 5. So we should produce negative according to our learn function. And that is correct. And look at the second instance. The first name is Peter. So the length of the first name is 5. So it is less than or equal to 5. So we produce a positive label. This is also correct. And if we examine further the third, fourth, and fifth instance, I will say, okay, the length of their first names are all 4, less than 5. So we produce positive labels, right? So it is all, they are also consistent. And in our final instance, the name is Michael Jordan, and the first name is Michael, and the length of first name is 7, right? 1, 2, 3, 4, 5, 6, 7. Yeah, I'm correct. So it's bigger than 5. So according to our function, we will produce a negative label. Looks like our function works perfectly, right? We have successfully produced the correct labels for all the training badges. So it looks like we are confident enough. We are confident to apply our learn function to give labels to the names outside of our training badges, right? But before we apply our learn function for the new cases, we should ask a few questions in R1. That's also what we should do when we generally we will carry out some supervised learning tasks. The first question is, are you sure you got the correct function? Our current function, which are perfectly in labeling all the training instances, but how many training instances in our do we have? Only 6, right? And how many possible names in a word could be billions? So are you confident enough that your learn function will correctly classify all the other like billions of names you have never seen? I think we may not be that confident. And the further question following this question is that if I want to increase my confidence that a learn function can do well in labeling those unseen instances or badge names, what kind of method we can choose, or what kind of strategy we can choose? An idea? I mean, still follow the exact same plain procedure. If I want to increase my confidence of my learn function, what kind of strategy can we use? Yeah, very good. Yeah, if I have not only six instances of our training badges, we have collected 6,000 training badges, and still we can work out a function that can correctly label all the 6,000 training badges, then we are much more confident, right? And later in our lectures, we'll give some rigorous description about the generalization capability of our learned function. I will say in this rigorous guarantee how the size of training data take effect. Okay, the second question is that what type of our learned function is? This function is just focusing on the mapping between the names and the positive or negative labels, or this function also considers some modeling or assumptions over the generation of names. Of course, in this simple function, we only consider the prediction step, right? We do not make any assumption, or we do not care any procedure that how the names are generated, right? So this function is simply a case of discriminative model. But in machine learning, as we'll learn in later lectures, we'll see that there are also a large class of machine learning models are called generative models. In generative models, we not only care about how we map the instance to some labels, we also care about how our inputs or how our instances are generated. A typical example is called naive Bayes, and which we will introduce later. And fourth question regarding the data representation. How do you know you should look at the letters of the names on the badges? How do you know you should use a length of the word to construct our function? Why we should use that? How do you know that those kind of features are useful for our prediction? And also, we choose the length of the word. That's our important feature to construct function, right? But how do you know a word has a length? This may be a stupid question because all human beings know that the word has a length. But it at least means that you have some background knowledge or prior knowledge. That is, all words have some length, right? For other problems, your background knowledge or your common sense knowledge may not be that explicit. But in that areas, we still will utilize our domain knowledge or domain specific or domain expertise to help us to find a good way to represent our data and to facilitate our learning function construction. And finally, we should consider how we arrive at this function. Because right now the learner is ourselves, so it may be hard for us to work out a algorithmic process to reach this function. But when you are designing or when you are developing a specific learning algorithm, you should consider this, right? Because you will instruct the machines to do that. So having those questions in our mind, let us look at what is supervised learning. So by thinking about supervised learning or by planning to use supervised learning to address our problems, we should first be very clear about what are our instances and what are our labels. And for example, our task is to automatically tag the news articles. Then what should be the instances? Yes, very simple, right? So the instance should be all possible news articles that need to be tagged, right? And what are the instances? Yeah, the tags. The tags would be the sports. Of course, we could have many tags like sports, business, politics, entertainment, and etc., right? And our task is essentially to find a mapping between some instance, namely a news article, to some label in our label space, right? So this is a concrete example about the automatic tagging news article. And in general, in a specific supervised learning task, we should first identify our instance space, namely the set of examples that need to be classified. And then we need to determine our label space, which actually determine exactly where the task is, what the prediction task is. And both instance space and the label space vary on different tasks. For example, if our task is to do the spam email filtering, then the instance space, what is the instance space? The emails, right? All possible emails. And what is the label space? Yeah, just two labels, spam, not spam. And in our badge scheme, what are the instance space? Yeah, names on the badges. And what are the label space? Positive or negative? Yeah. So given the instance space and the label space, we believe that there is some underlying target function which map the instance in the instance space to the label in the label space. And unfortunately, this target function we usually do not know. And the goal of our learning procedure is to find out this target function. So essentially, learning from the algorithmic point of view, it is a search process over all possible functions. And in supervised learning, we make extra restrictions on how we are going to run our learning algorithm. So specifically, learning algorithm are allowed to say a set of instances and their function values. More specifically, we'll prepare a set of training data, which consists of a set of instances and their function values. Then we feed this labeled training data to our learning algorithm. And after the execution of our learning algorithm, we expect our algorithm can produce a learn function, which is also a mapping between the instance space and the label space. So this is the whole protocol for supervised learning. So can you think of other training protocols or learning protocols other than this?
Other than supervised learning?
Yeah, other than supervised learning.
Unsupervised.
Yeah, you can. Yeah. So what do you think of the protocol for unsupervised learning?
You try and see, like, in your instances, which ones are similar to each other, so you can use some kind of like clustering.
Well, you are talking about details about the learning algorithm. But if we are talking about the general protocol for unsupervised learning, we can just remove those labels, right? Remove those ground truth function values. And we just feed the learning algorithm with a set of training instances. And to say whether if our learning algorithm can still produce a function between the instance space to some label space. And in many cases, for unsupervised learning, we even do not define the label space. And also we can do semi-supervised learning, right? We prepare a set of training data, but only give the labels for half the data. And the other half, we do not give the labels. And we feed it to some learning algorithm. Can our learning algorithm still produce a learn function? So now let us keep looking at our supervised learning algorithm. Suppose we have already had a learn function. And the next step is what? Evaluate, right? We want to say the quality of our learn function, or more accurately, we should say the generalization performance of our learn function. Ideally, if we know the target function, I mean the ground truth, we can directly compare whether the two functions are the same. But unfortunately, this is not doable in most of the cases, except if you are designing some toy problem. Then what should we evaluate? What should we examine?
The labels. You can train on like a subset of the instances, and then you can predict the instances that you left out, and then check if it predicts the same exact labels.
Yes. In other words, we draw some test example, right? We draw some test example from the instance space, and then compare our prediction with the ground truth function value. And if they are the same, okay, we have more confidence that our learn function is good. Otherwise, our learn function could be problematic. So in order to get a better or more robust estimation about our evaluation about the generalization performance, or in other words, quality of our learned function, we usually apply the learned model many times to predict on the test examples and compare with the target prediction. So now there is another question. Can we use test example during training? Or in other words, can we just use a subset of training examples to evaluate our learned function?
Yeah.
Definitely no, right? Because this is cheating. What is our objective? Our objective is to examine the generalization performance, or generalization capability of our learned function. What is generalization? It is your capability of performing a task in the cases where you've never seen, right? You have already you have already done very well in some same examples. Then you use those examples you have already done to examine your capabilities. That's not that means nothing, right? So this is a common sense. Never use test examples during training, or in other words, never sample any training examples for testing. So now let us look at the comprehensive general setting for the supervised learning. So to carry out any supervised learning task, we should first prepare the training examples. The training examples are essentially a list of the pairs, and each pair consists of the training instance and the function values. And this target function is usually unknown, usually very difficult to know. And typically, the training instance in machine learning is represented in some vector space. We call it feature space. For example, a specific instance could be represented by a n-dimensional binary feature vector, or n-dimensional real value feature vector, or some hybrid of them. And to get this feature vector representation in our machine learning algorithms, we usually have to use a deterministic mapping to map from the raw instance, the original instance, to the feature vector space we are going to use. And this process is usually referred as feature extraction, and which we will explain later. And for each training example, the value of the function, the target function value, is usually called label. But label is not necessarily discrete. It could be a continuous value. And given those training data, our goal of supervised learning to find out a good approximation for the target function f. In very rare cases that we can find out the target function. But actually, in practical applications, we usually can expect that we aim to find out a good approximation. And also, the training labels, the set of labels or label space determines the types of specific supervised learning tasks. For example, if our labels are binary, that means we only contain 2 elements in our label space, then our supervised learning task is called binary classification. If we have multiple labels, but we still have discrete labels in our label space, then we are doing multi-class classification. If our label space instead consists of continuous values or real values, this task is referred as regression.
What's the difference between the feature space and instance space?
That's a very good question. I will explain later. Yeah. Any other question? Okay. So given this general setting about supervised learning, let us further look at I should ask a question. Okay. What kind of scenarios or what kind of applications we could use supervised learning to help us to address problems? Here, just list a few scenarios. There could be many scenarios, but those scenarios are quite typical. First scenario where we can apply supervised learning is that there is no human expert. For example, the task for automatically identification of DNA binding sites. So DNA is a long sequence, right? The biologists have found that in specific locations in DNA, these locations are easier to attract molecules. So these locations are called binding sites. And although the biology researchers have found this phenomenon, we do not know why. We do not know how the mechanism for those specific DNA locations can attracting those molecules. But we still want to predict what kind of where are those locations which the molecules would like to attach. What should we do? Supervised learning, right? We use our microscope to collect a set of training data, which consists of different DNA and their binding sites. And then after the execution of a supervised learning algorithm, we expect our learned function, a learned model, can predict the binding sites for a new DNA. So this is one example. And a second example scenario is that if we want to do some task, humans can perform very easily, but can't explicitly describe how we do it. For example, to recognize objects in some pictures, we are very easy to do that. Like we are very easy to recognize people, desks, laptops, erasers, right? But we just can't write up the explicit instructions how we're going to do that. This is actually still unknown for neuroscience researchers. But in those cases, we still want some machines or robotics to help us to automatically recognize objects in images. What should we do? Supervised learning, right? We collect a set of pictures and we label the objects in the pictures. And this is the training data and feed them to some supervised learning algorithm and hope that our algorithm can automatically tag the objects in the images. So actually, this task is now the machine learning algorithm can perform very well, which is mainly based on deep neural network technologies. And third scenario could be the desired function is too complicated to obtain a closed form or an analytic form. For example, to predict the stock market price, we have developed. The researchers in finance have developed many complex and elegant mathematical theories, such as all kinds of random process, partial PDE, partial differential equations, etc., to characterize the perturbations of the stock prices. Even we can quite accurately characterize this, we're still unable to write an explicit function to describe what are the function values for different times or whatever. And sometimes we can even prove that there is no explicit function. Then what should we do if we still want to predict the stock price? Supervised learning, right? Okay, this is some problem with the device. That's fine. Okay. Supervised learning. We just collect the training data, which consists of different stocks and prices. Then throw them into our supervised learning algorithm. We hope we can then predict the price for some new stock. Right. So this is a few examples of where we can apply supervised learning algorithm. And using supervised learning algorithm, we should be careful about the following questions, or we should address those to ensure the success of our supervised learning algorithm. We should address those problems one by one. So let us look at what are those problems. First, how can we identify the instance space? This is the same thing you asked. How can we find out what is the general process for us to find out an appropriate instance space? And second, what is our label space? This label space accurately or precisely determines what kind of prediction task is, and also decides what type of supervised learning task it is. And what is our hypothesis space? So as we previously mentioned, learning from algorithmic point of view is a search behavior. It search over a set of functions. So we should need to specify what is the range of functions, what is the set of functions we're going to search over. And what is our learning algorithm? How can we design algorithmic steps to execute our learning procedure? This actually is referred to different learning algorithm, and we'll talk about this point by introducing the algorithm details for a bunch of classical learning algorithm. And along with this question, what is our loss function or evaluation metric? And in many cases, actually, the loss function is the main objective of our learning algorithm. That means the learning algorithm is essentially to minimize this loss function. And this loss function is also used as an evaluation metric to test our generalization performance. So now let us look at this problem one by one. First, the instance space. So this is the question I want to ask. Can we directly use the raw instance or the original instance and use them to fit to our machine learning algorithm? Any idea?
Maybe, but you usually use the features, right?
Yeah, why should we use the features?
It's in like for computer. It's in like a language the computer can understand. I guess. It's like a numerical
Yeah, exactly.
representation.
Yes, very good. For example, your task is to classify some piece of news in a newspaper. Then how computer program will do that? Computer program cannot directly read this paper, right? You cannot throw this paper into the computer hardware. For example, you want to classify whether I am a handsome man. You cannot directly throw me into the computer hardware because they cannot process human bodies. Right? They can only process numbers. So in our practical task, we must use a set of, or we must work out a set of numbers to represent our original instance. Except that our original instance is already the numbers, right? So we call this set of numbers which represent our raw instance as features. This is how the features are defined. And actually, this set of numbers, how you choose this set of numbers or how you work on this set of numbers are very important for the subsequent success of our learning task. And here I want to give you some examples about features, like Bloom features. For example, if our task is to predict the spam emails, so we can work on the Bloom features such as, does this email contain the word free? Sounds pretty reasonable, right? We can also work on a feature like, does this email contain a word like greetings or etc. And we can also invent some real better features, like what's the height of the person? We want to predict whether this person is handsome or not, right? And what is the weight of the person? Maybe, but this is quite private part if you can have such kind of data. And also, what was the stock price yesterday? It could be used for our prediction task in predicting stock price, right? And what's the length of the word? Can be used as a feature in our badges game playing, right? So to generate those features from our original instance, we usually use this so-called feature function. So feature function is essentially a mapping between our raw instance, such as emails, names, images, to some feature vector. And feature function is also known as feature extractors. And usually this is some deterministic mapping, but there are some exceptions. For example, in the recent years, there's a hot research topic called random hashing to dramatically reduce the dimensionality of data. That allows to to incorporate some randomness. But in our class, we only focus on deterministic feature hashing. So after we apply the feature functions to convert our original input to some feature vector, then in our machine learning algorithm, this feature vector is used as an instance. So this is the process how we produce features. Any questions? Okay. And then, because our instance now is represented by feature vectors, then the instance space is now become a vector space, right? Say a n-dimensional. If you're extracting binary feature vectors, then our instance space will be a binary vector space, right? If our feature space, if our feature vector is a real value vector, then it is a real vector space. Our instance space will be a real vector space. And an important geometric view is that the feature vector can be considered as a point in our feature space or instance space. For example, if our feature function generates two-dimensional features, and then each feature vector, or in other words, each specific instance is actually a two-dimensional vector, which corresponds to one point in our instance space, right? So this geometric view is very important for us to understand some classical classifier, supervised learning classifier I will mention later, like a support vector machine. So just to keep in mind that's this geometrical interpretation. So now, let us brainstorm some features on our badger scheme.
Can we have like matrices or other higher ranks tensors as the inputs as the feature? I mean, instead of vector, we have like two-dimensional structure.
Yeah, you can do that. But actually, you're intentionally make the problem more complicated.
Okay.
Because even you are using matrix, if you stack all the rows, all the columns, it is still a vector, right?
Yeah.
So vector is the most general representation of the features. But definitely you can use matrices to do that.
But it usually makes it harder.
What?
It usually makes it harder to
It's not saying hard. We just want to use a simple and a general notation or representation to denote the instance. Because matrix, from my point of view, you can consider matrix just a special form of the vectors, because you can convert matrices to a vector. And there's in most of cases there's no differences when you deal with the two problems. But when you're I want to tell you, in work cases, you can consider a matrix representation. That means there are some correlations between the features, and there are some specific structures you want to impose or you want to explore in the feature vectors. You may consider that matrix representation could be more beneficial, but in the most general case, we just use feature vector to represent our instance. Okay. So let us look at our first binary feature, which we can design for the badger scheme. This feature could be the second letter of the name. To see it, let us look at the first instance. It is Nokia, right? So the second letter is A. So we can use a binary vector to represent this letter A. And the first dimension is 1, and all the other dimensions are 0. Because because A is the first letter in the alphabet, right? And in the second instance, and the second letter of the name is B. So in our feature vector, the second dimension is 1, and all the other dimensions are set to 0. And the third instance, Manny has the same feature vector as Nokia. And in the fourth instance, the second letter is C. So in our feature vector representation, the third dimension is 1, because C is the third letter in the alphabet. So here comes the question, how long is this feature vector?
26.
Yeah, 26, right? Because we have 26 unique letters in our alphabet. And this is one example of the feature vector. And oftentimes when we design feature functions, we just treat it as some templates. And when we apply our feature function on different instances, it is just a different template instantiations, right? And in addition to binary features, we can also come out some count value features or real value features, such as the length of the name. Like for this instance, the length of the name is 5, and for this instance, the length of name is 3, right? And actually, we can use multiple feature functions. And each feature function can produce a feature vector. And finally, to represent the whole instance, we simply concatenate all the feature vectors produced by the feature functions we use to form the final instance representation. That's a longer feature vector. Right? Okay, this is pretty much all about the process for us to do to identify the instance space. But we need to know that good features, or in other words, good feature functions are very important for us to carry out, for us to ensure our supervised learning to be successful. If your features is bad or meaningless, it could be useless or even harmful for your learning algorithm. For example, here I give a bad feature function for our badge scheme. This feature function is there a day of the week that begins with the last letter of the first name? Sounds absurd, right? And in practical applications, we have to put much effort in designing features. And this step is usually referred as feature engineering. And in many, in some tasks, very tricky, then human designing for the features might still not be good enough. Then what should we do? We learn that. Recently, in several tricky tasks such as image processing and voice recognition, those effective features are totally learned by machine learning algorithms, more specifically by deep neural networks. And in our lectures, we will touch upon several general principles for designing good features, but those features but the definition of the features are largely domain specific. That means to design a good feature, you have to use your domain expertise, which is highly reliant on different tasks. So just keep in mind all those points. So now, let us look at the second problem we need to consider about in deploying our supervised learning task. That is, what is our label space? So why we should care label space? First, it helps us to well-define the problem. If we do not know what is our label space, then we cannot carry out our prediction task, right? The second thing is that different label space actually correspond to different types of supervised learning tasks. And each type of supervised learning task have a set of specially designed learning algorithm. So to be careful about label space is important for us to choose the appropriate learning algorithms. Here I just give the simple categorization of the supervised learning task according to different label space. If our label space are discrete, that means it contains finite discrete labels, then this task is generally referred as classification. If it only contains two labels, this is binary classification. And in the whole semester, we will primarily focus on binary classification. And we might see a bit of multi-class classification. That means we have more than two labels. We could have k possible labels. And sometimes in more complex cases, where our labels consist of structures, like some graphs, then our task is called structure classification, which is heavily used in natural language processing. But our label space could also be numerical or continuous. For example, if our label space consists of real numbers, then our supervised learning task is regression. And further, if the labels in our label space contain some ranking information, like you put a 5-star review on Yelp, then that means it is slightly different from a 4-star review because they both indicate you are quite satisfied. But it's very different from a 1-star review. That means you are very unsatisfied. If we want to consider this ranking information and predict these labels, the task is really referred as the ordinal regression. So this is pretty much I want to talk about the label space. And now let us look at the third problem. What is our hypothesis space? Namely, what type of functions or what family of functions we are going to search. We are going to let our learning algorithm search. So, as we defined earlier, the goal of learning is essentially a way to find a target function, this target function, or find a good approximation of target function. So the learning process is actually a search over functions. Before the search, what should we do?
Define which functions we're going to look at.
Yes, definitely right. We must know the range of functions we are going to search over, right? So the hypothesis space is a set of functions we consider our learning algorithm to search. An important problem for design a learning algorithm is that how can we decide the hypothesis space? To see the importance of this problem, let us try to learn some simple functions and by considering different hypothesis space. Suppose now our task is to learn a function, and this function consists of 2 binary input variables, and our output is also assumed to be binary. And we now consider all possible such kind of functions. That means all possible Bloom functions with 2 binary input variables. We want to search over the full space. Sounds pretty good, right? This is some way we can guarantee we are able to, we are possible to reach the ground truth function. And let us look at this simple case, and we have 4 label training examples. So can we learn this function? We can, right? Because to identify a Bloom function with 2 input variables, how many function values should we determine? 4, right? Because each input variable has 2 possible values, 0 or 1, and we have in total 4 possible combinations of the values for those input. And for each value combination, we should have 1 function value, and so we should have 4 function values to determine to specify one function. And we have 4 training examples. So we just fill out this function table to get 1 function. And since we are good, looks like we are nice, we are safe. Now let us think about a new case where we have 4 input features. Still, those 4 input features are binary. And our output function are still binary, right? And we're still searching over the all possible Bloom functions. And looks like our assumption is very nice, very good. We do not miss any possible functions. And also, we increase the number of training examples from 2 to 7. This sounds reasonable because we double the size of the input features and almost double the size of the training data. So now comes the question, can we learn a function by searching over the full hypothesis space? To think of it, let us first consider to determine one function, just to determine one function, how many function values we will need to identify this Bloom function with 4 input variables. 16, right? Each function value, each input has 2 choices. We have 4 binary inputs. So we have 16 combination of input values, right? For each combination, we should determine 1 function value. And how many training instances do we have right now? 7. That means to specify just one function, we still have 9 entries in this function table unknown. That means if we search over all possible Bloom functions with 4 input variables, we cannot use these 7 training examples to identify even one function. Where's the problem? What's the problem?
It's underspecified.
Not enough examples. Okay, yeah. Looks like this sensible solution. We can simply increase the number of training examples from 7, say, to 16. Then at least we can determine one function. Or in other words, we can specify, we can locate one function in our hypothesis space, right? It looks like this is very easy for our 4 binary feature case. But what if we increase the number of features from 4 to 100? Then how many features, how many training examples we need to determine one function?
2 to the 100.
2 to the 100. This is a huge number, right? But I can tell you in practical applications, 100 features is really, really small. If you use 100 samples, 100 features to address one practical problem, people may criticize that we are doing a toy example. And like I'll give you an example of a typical application like in online advertising. An important task is called click-through rate prediction. And we just want to predict whether a user, when they see a piece of advertisement, whether they are gonna click on it. This is a binary prediction, right? The output labels predict, and then we can also generate a lot of binary features. So in this type of tasks, we at least have to process millions of features, and oftentimes we'll have billions of features. So if we search over all possible Bloom functions, then we should at least prepare like 2 to the millions or 2 to the billions of training examples. Even we have a lot of computer clusters or computer hardwares, it is still not feasible for us to prepare so large training data. So it looks like simply increasing the size of training data cannot address our issue, right? Any other solutions?
Diversity data?
Diversity data.
Yeah, make sure that the vectors that you're taking in don't, let's say you have 7 vectors and they all vary in the same kind of area, but the majority of the vector looks the same. That makes sense.
I'm not pretty clear about this.
Okay. If you have, make sure that a lot of your examples don't look the same, is what I'm saying.
Yeah, but in the 7 examples, those examples are all different.
Right. Oh.
But you can make another assumption that you're looking for permutations versus combinations.
Yeah, your answer is closer. So in general, we cannot use very, very large hypothesis space, right? We can see we have already seen the consequence of doing this, right? If we use the full space, of course we won't miss this correct function, but the side effect is to identify even only one function, the size of training data will grow exponentially to the number of features. So how should we solve it? Reduce the size of we reduce the size of the hypothesis space. We do not choose that large hypothesis space. For example, we can restrict the form of functions we are going to search for. And here I list a few simplified or reduced hypotheses, like simple conjunctions. Simple conjunctions are a specific type of functions which have the form that they are simply conjunctions between a set of variables. So it is much more restrictive, right? And simple disjunctions is just a set of disjunctions between variables. m of n rules. That means when we fix a set of n variables, at least m of them must be true. The m of n rules, then the function values will be true. And let us say, if we reduce the size of hypothesis space, what's the effect? Or what kind of effect on our learning algorithm? First, let us try this simple conjunction hypothesis space. So conjunction rules or conjunction function forms is like this. For example, I choose 3 variables, and the function is defined as xi conjuncting with xj conjuncting with xk. So let us first look at how large is this simple conjunction hypothesis space. An idea? So we have 4 variables in total, right? If we write down the hypothesis conjunction for the 4 variables, it's like this, right? But we can choose whether we exclude or include this specific variable in our conjunction, right? So for each variable, we have 2 choices. So how many choices we have in total? 16, right? Each choice correspond to a specific conjunction function. So in our simple conjunction space for this simple 4 variable case, what's the size of hypothesis space? 16, right? Because we have in total 16 functions here in all possible simple conjunctions. So the size of hypothesis is 16. And now let us go back to consider if we do not make any restriction of the hypothesis space. If we search over the full hypothesis space, I mean all possible Bloom functions with 4 variables, what's the size of hypothesis space? So if we do not make any restriction to determine a Bloom function with 4 variables, how many function values we should determine? 16, right? Each specific function actually, why is market so bad? Each specific function, Bloom function with 4 variables actually correspond to a function table, right? And x1, x2, x3, and x4, and this is function value. And we have 16 possible combinations for input variable values, right? So we have 16 entries need to identify to specify one specific function. So each function entry, each function value has how many possible values for each function value? 2, right? So we have for each function value we have 2 choices. And then for 16 function values, how many function values we'll have? 2 to the 16, right? So the hypothesis space for the full Bloom function with 4 input variables is 2 to the 16. Right? This is 16,536. It's much larger than the size of our simple conjunction hypothesis space. Right? Looks like we have successfully reduced the size of hypothesis space. Is this hypothesis space and then better? To see it, let us look at whether we can find out. This is let me first list all the 16 hypotheses or 16 functions in our new simple conjunction hypothesis space. Then, to see whether this hypothesis space is good, let us look at whether we can find out a good function which can correctly produce the labels for all the training instances. Can we do that? We can examine those functions one by one, right? And unfortunately, sorry, I wanted to do some example further. So how many simple conjunctions are possible when there are n inputs instead of 4? Yeah, 2 to the n. Yeah. 2 to the n, right? It's very simple. So we can examine whether we can find out a very good function which can explain the training data well. We see whether it is consistent with the training data. And after examination, sadly we found out there is no function in our simple conjunction hypothesis space can perfectly explain the data. And those are all the counterexamples. For example, this function is x4. That means only when x4 is 1, then the function output is 1. And we can say this training example 0, 1, 0, 1. So according to our function, the value should be 1, right? But let us look at the our training examples. 0, 1, 0, 1, 0, 1. The true label is what? 0. So it's different. We're making mistakes. And we can look at another example of the function in our simple conjunction space, like x1 conjuncting with x3 conjuncting with x4. And look at this example. It looks like because x1 equals to 0, so this conjunction value would be 0. Right? But let us look at our training examples. 0, 0, 0, 0, 1, 1. The true label is 1. So what's the problem? Why we cannot find out a very good function in this simplified hypothesis space?
Your search just
Bad guess, I guess.
Yeah. You are too extreme, right? You simplify too much. You reduce the size, the possible size from the 65,536 to only 16. That is easily the problem that you can never find a reasonable well function. Then what should we do?
expand slowly?
Yes. Yes. Very good answer. Yeah. Our hypothesis is too small. And it's so small that we can even find out a reasonable well function which can explain the training data well. So what should we do? We should expand our hypothesis space to be, say, a little larger, to be more expressive, to be more flexible, right? So now we switch to a second hypothesis space called M of n rules. So the M of n rules specify a function, a kind of function that for a subset of n variables, the function value equals to 1 only if at least m of those variables are 1. For example, we choose 3 variables, x1, x3, x4, and we set m equals to 2. Then in this 2 of 3 rule, I mean 2 of 3 function, only 2 of the variables from x1, x3, x4 are 1, then the function value is 1. Otherwise, the function value is 0. So we first check whether this M of n rules hypothesis space is larger than our simple conjunction hypothesis space. How can we make sure that it is larger? We can calculate the hypothesis space size, right? Let us look at how many functions in our M of n rules hypothesis space. Anyone give some hints in calculating the size of hypothesis space? All right, let us look at this problem. So first we should choose n variables, right? For each fixed n variables, how many values of m can we choose? We can choose m equals to 0, 1, 2, to the n, right? But we need to be careful about the case that m equals to 0. Because when m equals to 0, what does that mean? Oh, great, thank you. Okay. Very good. Okay. When m equals to 0, according to the definition of M of n rules, at least n variables are 1, then the function values are 1. So at least zero variables are 1, then the function values are 1. What does it mean?
Always true.
Yeah, that is always true. So no matter how you choose the n variables, the function values are always true. So for the case of m equals to 0, it corresponds to a unique function, one unique function, no matter how you choose n, right? So let us just put aside this case that m equals to 0, then consider other cases. So here, we specify that m can choose 1, 2 to the n, right? Then for our 4 variable case, how can we choose n? N can be 1, n can be 2, n can be 3, n can be 4, right? And how many choices of the n variables? C for n, right? That's a combination. That's a number of combinations, right? To choose n variables out of 4 variables, right? And given one specific subset of n variables, and how many m can we choose? Because each m corresponds to a different function. We have m can be choosing from 1 to n, so we have n choices, right? So this is for one specific n, and because when n can be ranging from 1, 2, 3, 4, so to calculate the total number of m of the rules, we just summation n equals to 1 to 4, right? And finally, we just plus the case that m equals to 0. Because m equals to 0 corresponds to all true. Right? So when we calculate this simple formula, we'll get this number is 33. So how large is the hypothesis space for our m of n rules? It's 33, right? And what is the hypothesis space for our simple conjunction rules? 16, right? Looks like we have already found a larger hypothesis space. It should be more flexible. So then what's the next step?
Check it, evaluate.
Yeah, we check whether in our 33 functions, can we find out reasonable well functions, which can be consistent with the training labels, right? I will leave this task for you. And actually, I can tell you the answer. There is only one function which can explain this data well. One function is enough, right? It's at least much better than we cannot find any function in simple conjunction space to explain data well. Right? So through those 3 cases, now we use 3 different hypothesis space to carry out our learning procedure. What kind of conclusions can you draw from this process? What's your thinking? Any ideas?
I mean, there are a lot of possible solutions because we don't have the full function definition, but we found one. So
Yeah. So when we restrict the search space, usually we're unable to use the full space without any restrictions. And the consequence, we have seen that sometimes we even do not have enough data to even identify one instance, one function in the full space. So we have to restrict the search space before we deploy our learning algorithm, or before we develop the learning algorithm. Then here comes a problem. How do we pick such kind of hypothesis space? And unfortunately, there is no unique answer to that. If you have some prior knowledge, you can do that, no problem. But if you do not, usually we can only guess. If the hypothesis space you choose is too small that nothing in this hypothesis space that agrees with the training data, what should we do? Yeah, it's a tentative, right? Then we need to choose some more flexible hypothesis space. And then we can test, we can say whether in this more flexible hypothesis space we can find out a reasonable well function. So this is a kind of a trial failure procedure. But we should keep in mind that there is no unique solution. There's no unique guarantee that we can find out an appropriate hypothesis space. And actually, this kind of hypothesis can depends on your applications. So the general strategy for our K-R learning algorithm is that we first try to take an expressive hypothesis space, and we hope that this hypothesis space can contain the target concept. By saying concept, I mean the target function or target classifier. Sometimes we may call it oracle. And here are a set of hypothesis space. But ensure that our hypothesis space is expressive enough, but we cannot make it extremely large. Otherwise, our learning algorithm will not be feasible. Then we develop an algorithm that can find such an element in a hypothesis space that fits the data well. Then we hope it can generate well in our same data. So this is a whole procedure that we develop the learning algorithm. And there could be some pessimistic conclusion that there is no unique solution to help us to find out the correct or the appropriate hypothesis space. That's kind of bad. But as we learn some computational learning theory, like pack learning, in the later lectures, we'll see that even our hypothesis space is not correct. We can always, in some conditions, to find out some guarantees that ensure we can have a high probability to obtain a learned function which is not far away from the predictions generated by the ground truth function. So don't be so pessimistic. We still have a big chance to win. So now let us step back to take a look at the learning procedure. So essentially, the design of learning algorithm or the running of learning algorithm is a process of removal the remaining uncertainty. At the beginning, we must make assumption about hypothesis space, right? And then they identify some specific instance or specific function in our hypothesis space is actually the process of removing the uncertainty. And how are we gonna remove those uncertainty? Based on which we remove the uncertainty? Through training data, right? The training data help us to throw out those bad functions, those inappropriate functions in our hypothesis space to find out the best function which can fit the data. And also, designing a learning algorithm requires us to guess a good enough but small hypothesis space. And we should keep in mind that our guess might be wrong. And we could find a consistent hypothesis that explains the data well, but still be incorrect with the new example. Just keep in mind about this. But later, we'll find some positive conclusion or optimistic conclusion that we have a large probability to obtain a hypothesis which, although it is different from the ground truth, but we will still obtain good generalization performance. Okay, that is pretty much I want to mention about today. And regarding the remaining two questions, what is our learning algorithm, and where's our loss function and evaluation metric? I want to explain those problems by introducing different classical machine learning algorithms. So from next lecture, we'll introduce the first classical learning algorithm called decision trees. And see you next Monday. And remember to look at the next Wednesday. Next Monday is holiday. Okay. Sorry, I didn't.
Do you have me on the?
Remember to look at the camera for the first homework.
On the webpage, previous links on there. All right. I was like, no way.